Welcome back everyone. In this lecture we will continue with the symmetric and alternative products. So we already we have seen that there are many equivalent definitions of these symmetric products. So let me actually continue with that. So I am going to give one more definition of symmetric product using this symmetrization map. So let us recall what is this TV, which is the tensor algebra. So you take this TV, which is the tensor algebra, where you have taken the direct sum of these graded spaces. So this TKV is nothing but the k-fold tensor product. So this TKV is indeed the k-fold tensor product. So now what one can do, one can actually define this natural symmetrization map from this TKV to TKV. So let us call this as pi symmetric, so which is called symmetrization map. So this is what called symmetrization, so which is a map from TKV to TKV. So how it is defined? So let us define it on only on the simple tensors. It is a linear map, so which is given by, so this is to begin with just a C linear map. So which is given by, you take this simple tensors V1 tensor etc. Vk, and then you send it to this symmetrized version of that. So you average to over k factorial and then take the sum running over all sigma in Sk, where you just act the V1 tensor etc. Vk, you act sigma on that V1 tensor etc. Vk. So then we get this V sigma 1 tensor etc. V sigma k. So this is what called the symmetrization of this V1 tensor etc. Vk. And it is not very hard to see that this is indeed element of this sim k of V that we defined before. So basically, so one can take this as a fifth definition. So indeed the sim k of V is nothing but the image of this pi sim. Okay, maybe let me put k here to say that it is happening at the level of k graded base. Okay, so this you can take it as fifth definition of this sim k of V. So we already defined so many definitions. The most important thing is, so it's most important thing is we have this SKV, and which is naturally isomorphic to sim KV. And if you think about it, so what we have done, so we have actually kind of factored this TKV into this sim KV direct sum some other, let us say WK. So now you have this quotient map from TKV to this SKV, and we are saying that we have this factor of this quotient map. So let us call this map pi. So we have this factor map, maybe we call this as pi sim k. So if you think about it, it is actually kind of natural map only. So what is this map indeed? This, maybe let me use some other notation, pi tilde k sim, which is a map from SKV to this sim kV, which is given by, you take V1 tensor etc. Vk and then just send it to this symmetrized product 1 divided by k factorial, where sigma runs over Sk, and then V sigma 1 tensor etc. V sigma k, and this is indeed an isomorphism. and one can check that it is indeed surjective map from SKV to SimKV, and since both have same dimension, so this will be actually isomorph. So maybe I will leave it as exercise, so one can check this. Okay, so this is actually concludes everything about the symmetric product. So now let us focus on this alternating product or the exterior product. So let us define what is this exterior algebra and then exterior product. So like we did it in the symmetrization, so here what we are going to demand, so we are going to demand that x square is 0 for all x in V. So basically if you think about it, in TV we did not have any relations among the generators x1 etc. xn. In S of V we demanded that all the generators x1 etc. xn they commute. Now we are going to define this lambda V, which is the exterior product. So we are going to demand that x square is 0 here in lambda V for all x in V. So here no relation, here only the commutation, and here we demand x square is 0 for all x in V. Okay. So more formally, so what you do, so lambda V is defined to be, you take this TV and then you go modulo the two sided ideal generated by x tensor x for all x in V. You take this two sided ideal generated by x tensor x for all x in V. And we usually denote the image of this x tensor y in lambda V as x wedge y. So this x tensor y, this image is denoted as x tensor y. So let us say we have this quotient map, maybe call this quotient map Q to lambda V, and Q of x tensor y is usually denoted by x wedge y for all x y in capital V. So we can also talk about k-fold product. So maybe let me just write it. So even if you take some k-fold product, x1 tensor etc. tensor some xk, and then the image will be denoted by x1 wedge etc. wedge xk for all x1 etc. xk from capital V. So now note that x tensor x is 0 for all x in V. So that means, so here is the observation, if you take this product x1 tensor etc. xk and look at its image, so which is the wedge x1 wedge etc. wedge xk, and this is non-zero, would immediately imply that these xi's that appear here, they must be distinct. This x1 etc. xk must be distinct. If they are not distinct, let us say at least two of them are equal, and if they appear at the ith and jth position, so let us say something like this happens, wedge xi, wedge etc. wedge xi. So then what one can do, one can actually like bring this xi closer to this xi by switching. So if you switch, all you get is actually the negative sign. So up to a sign, so you can actually switch this x's and then you can actually bring it closer, then you will get something like this. And in that case you can see that whenever xi appears next to each other, then this is going to be 0. And how are we going to justify? The switching is going to give negative sign. That will simply follow from this following relation. Suppose if you are taking x wedge y, and then if you switch this x and y, then what you get is actually minus. So, this can be verified as follows. Look at this x plus y wedge x plus y, then since this wedge product is actually bilinear because we are going modulo this two sided ideal. So, what we got is actually an algebra. So, this is indeed a C algebra. So, the product must be bilinear. So, in particularly this x plus y wedge x plus y is going to give us x wedge x plus x wedge y plus y wedge x plus y wedge y. Now, since x wedge x is 0 and y wedge y is 0 and this is also 0. So, that is going to give us that 0 equal to x wedge y plus y wedge x, and that indeed gives us the relation that we wanted. And this is something one can check for any k wedge. Suppose if you take x I1 wedge etc. wedge x I k. So, maybe let me relabel as 1 to k, not a problem. And then if you are going to switch I and j, so then what would happen? It just gives you the minus sign. So, let me rewrite this. So, I will leave it to you to check this. So, you have xi etc. wedge xj etc. wedge xk, and then if you switch this xi xj, what you get is the minus x1 wedge etc. wedge xj wedge etc. xi wedge etc. wedge xk. So, you get minus sign here. So, more generally if you apply this symmetric group action, so then if you permute them, then what you can check. So, maybe this is the most general exercise, let me write it here. So, you look at the elements x1 etc. xk from V, then so let us take some sigma from sk. So, now there are two ways you can make a product. So, one is you can simply take x sigma 1 wedge etc. wedge x sigma k, and this is going to be exactly equal to. So, all you do is actually simple permutations. So, now any permutation can be written as product of transposition. For each transposition we have actually checked only minus sign is coming out. So, that means when you apply this sigma on this indices 1 to k, and if you take this x sigma 1 wedge etc. x sigma k, and this is going to be exactly equal to the sign of sigma times x1 wedge etc. wedge xk. For example, the way you prove this, maybe you can write sigma as a product of what is called the simple transpositions. So, what are the simple transposition? Transposition corresponding to I plus 1, they are called the simple transpositions, where I will run over from 1 to n minus 1, and it is easy to see that. So, this is going to generate our sk as a group. Okay. So, that means any transposition can be obtained by product of these simple transpositions. And now it is easy to verify for simple transposition. Whenever you switch xi and xi plus 1, you will get the minus sign. So, that is easy to verify. That is actually indeed this proof, x wedge y is same as minus y wedge x. So, that actually tells you that even for any general sigma in sk, you have this relation. Okay. So, this is actually kind of tells you that when you take this capital X1 etc. xn to be a basis of capital V, so then if you take any wedge product of size more than n plus 1, then that is going to be 0. So, that means lambda k of v is going to be 0 for all k greater than or equal to n plus 1. So, lambda k v is indeed 0 for all k greater than or equal to n plus 1. So, let me sketch the proof. If you are seeing the exterior product for the first time, you have to repeatedly use the fact that x square is 0. That means the product x wedge y is same as minus y wedge x, because we are working over characteristic 0 field. So, it does not matter, these two are actually indeed equivalent. So, x wedge x is 0 for all x in V is equivalent to saying that x wedge y is same as minus y wedge x for all x y in V. So, these two statements are equivalent because we are working over characteristic 0 field. So, now let us see how one can actually prove this. So, since what is this lambda of k? So, let me just recall the definition. So, this is naturally the image of TKV. Okay. So, that is your the lambda of k. So, recall there is this quotient map from T of V to lambda of V we have, and then this is indeed the direct sum of TKV, k range from 0 to infinity. Since the ideal that we are going modulo, so that is indeed graded ideal because it is generated by x tensor x. So, this quotient lambda V is also going to be graded. So, this is indeed direct sum of this lambda k V, k range from 0 to infinity. So, now you can see that what will be this lambda k V. So, the lambda k V, it will be generated by all the images of the k fold tensor that you are getting it from TKV. Suppose if you denote again this the image of your capital Xi to be small xi. So, maybe we can use Ya as well. So, let me see whether what I have used. So, let us use, okay. So, let us fix this capital X1 etc. Xn. So, this is as before basis of capital V, and then Q of Xi to be Ya. Okay, this is the notation that I am using. So, then it is clear that Ya square is 0. So, now it is easy to see that. So, this is going to be spanned by this wedge product of yi1 etc. wedge yik, where I1 etc. ik, this you can arrange it in the increasing order. So, now if you actually take this yi1 etc. yik, so if they are not in the correct order, if you switch them, then up to a sign you can make it correct order, because this is what this exercise says. If they are not in the correct order, you switch it in the correct order, then all you get is only the signs. So, that means you can always write it in the correct order, like I1 less than or equal to etc. ik. Now, suppose I1 and I2 they are equal, then what would happen? Then yi1 will appear next to each other, yi1 wedge yi1. So, that will become 0. So, that actually tells you that no two elements should be repeated. So, using that you can see that these inequalities indeed becomes strict inequalities. So, you can actually put this restriction on I1 etc. ik. So, this I1 must be strictly less than etc. strictly less than ik. So, the indexing set, now you take wedge y1 etc. yik such that 1 less than or equal to I1 strictly less than etc. strictly less than ik less than or equal to, and this set is indeed the minimal spanning set for your lambda kv. So, in particular this is indeed basis of this. So, this is indeed basis of lambda kv. So, I will leave it as exercise to check this. So, now once we know this is indeed a basis, then it is clear that when you have k is greater than or equal to n plus 1, then there is no way you can choose indices from 1 to n which are strictly increasing. So, that tells you that this set is empty. So, this set is empty. So, that implies immediately that lambda k v is indeed 0 for all k greater than or equal to n plus 1. Not only that, when k equal to n, then what happens? So, when k equal to n, then only choice that we have for I 1 etcetera I k is just this 1 less than 2 etcetera less than n. So, that means this lambda n v is indeed span of this y 1 wedge etcetera y n, y 1 wedge etcetera wedge y n. So, this one element is going to span this lambda n v. What's about lambda 0 v? So, lambda 0 is going to be the complex numbers, lambda 1 v is exactly equal to v, and lambda 2 v, which is the interesting one. So, this is going to be given by y I wedge y j, where you take the indices I less than j between 1 to n. And from this it is easy to see that the dimension of this lambda k v, so the dimension of lambda k v is exactly the binomial coefficient n choose k. So, this is indeed the dimension. For example, the dimension of lambda 2 v, because we are picking I less than j from 1 to n. So, this is n choose 2. Okay. So, what is the universal property of this lambda v? So, as before, so we have very similar universal property that we have seen for tensor product and symmetric product. So, let me just write down the universal property and then I will leave it to you to check. So, here is the universal property. So, if we are going to look at this lambda v, so as before, so we have this inclusion I from v to T v, and then we have this natural quotient map from T v to lambda v. So, let us take this composition, call it I tilde. So, that is the inclusion that we are talking about from v to lambda v. So, I tilde of v is going to be exactly lambda 1 v, which is isomorphic to v. So, this is indeed inclusion. So, let us call this as I tilde. So, now we have from v to lambda v the map I tilde. Now, given any map v to capital A, so let us call that map alpha. So, where what is this alpha? Alpha, as before, it is a C linear map. And what is this capital A? This capital A is indeed an associative algebra. Associative C algebra. But what we demand that this alpha satisfies this following property. So, let us say alpha is a given C linear map from V to capital A such that alpha V square is equal to 0 for all V in V. If this is given, so then what we can conclude? We can conclude that there exists a unique alpha bar such that, which is the extension of alpha, such that this diagram commutes. So, what is this alpha bar? This alpha bar is indeed C algebra homomorphism. So, this is indeed C algebra. So, this is indeed C linear map, and we have these two are C linear map, and this is in this is an associative algebra satisfying this property. So, and now it is not very difficult to actually see that such extension is possible given this condition alpha v square equal to 0. The proof is very similar to what we have seen in symmetric algebra. So, maybe we can assume that this is unital associative algebra, because we want to extend this v to tv, and then we have to factor through this lambda v to a. So, that is possible given this condition alpha v square equal to 0. So, as before, like one can have various different definitions of this exterior product. So, let me just give you two definitions. So, I am not going to give other definitions. So, here is the exercise. So, using the action of this symmetric group on the K tensors, so you can actually prove that this lambda Kv is as a vector space is isomorphic to those tensor products K fold tensor products X in V tensor K, such that when you apply this sigma on X, so what you get is the sign of sigma X for all sigma in Sk, and this is what you called as alternating tensors. So, this is what called alternating tensors, of course alternating K tensor. Usually this is defined to be alt K of V, and we have again this anti-symmetrization map. So, one can use this anti-symmetrization map also to define this. So, let us call this pi k anti-symmetrization, which is a map from TKV to this TKV. What is this map? You take this K fold tensor and then send it to its anti-symmetrization version. So, take V1 tensor etc. tensor Vk and then send it to this, again sum it over all sigma in Sk, average it to over K factorial, and then now take this signed sum, sign of sigma V sigma 1 tensor etc. V sigma k. Okay. And it is not difficult to see that the image of this anti-symmetrization map is exactly the alternating K fold tensors. Okay. So, and these two actually gives you two different definitions of the same this exterior K product or the alternating K product. And indeed what to note, so you have this natural quotient map from Tv to this lambda V, and that you can restrict to K. So, now this this result indeed tells you that this is actually has a factor. So, you can identify the image of lambda of K V inside this TKV, and the image is going to be exactly this alternating Kv. Indeed, what one can prove that when k equal to 2, so you get actually this symmetric twofold product and this alternating twofold products, they will actually factorize this two tensors. So, this is indeed a very important result about bilinear maps and so on. So, if you take tensor product of this V, tensor V, so then this is indeed given by the symmetric product V plus the alternating product V, and this is indeed not very difficult to actually prove. So, if you think about it, what is the dimension here? The dimension of this is going to be n square, and dimension of this is exactly n into n plus 1 by 2, and this one is going to be dimension n into n minus 1 by 2, and when you add these two you get exactly n square. So, both of them are indeed subspaces, that is easy to see, and the dimension matches. So, it is enough to prove that V tensor 2 is sum of these two spaces, and that just follows from this following basic identity. So, if you take xy in capital V, then if you take x tensor y, you can write it as just x tensor y plus y tensor x divided by 2 plus x tensor y minus y tensor x divided by 2, and this is going to be in the symmetric 2 of V, and this is going to be in the alternating 2 of V, and this proves that V tensor 2 is indeed sum of these two spaces, and since it is the sum and the dimension indeed matches, so this has to be direct sum, there is no other option. So, that actually indeed proves this exercise. Okay, so this is all I wanted to actually tell about the symmetric tensor and the alternating products. So, in the next class what I am going to do, so I am going to actually define the group action on these tensor and the symmetric and the alternating products, and then we will make them as G representations, and then we will see how those G representations help us to understand the general theory. So, if we start with V being G representations, and this actually gives us many interesting examples of G representations by considering the symmetric products, alternating products and so on. So, that is what we will be seeing in the next class. Thank you. I will stop.